video lecture going to be discuss the topic called basic processing unit as a part 1, which comes under the model 5. So it is going to be discuss some of the aspects which related to the basic processing, especially in the central processing unit. So the presentation milestones are as follows. At the beginning we will going to be discuss the instruction set processor, that is a ISP, and going to be discuss that central processing unit. So that going to be comprises the processor and other control signal generations, so it's going to be participate as a part of the central processing unit. So that is the other aspects we are going to be discuss, that typical computing task consists of a series of steps specified by a sequence of machine instructions, so that constitute a program. So program comprises the set of instructions, so those are sequenced of machine instructions going to be generated after the compiling. So the code will be going to be set of instructions going to be taken care here, series of steps to be specified, and at the end that is instructions is executing by the carrying out a sequence of more rudimentary operations. So that is also going to be discussed further, going to be discussed that how control signal generation with the help of this processor. So at the beginning, that is a fundamental concept. Processor fetch one instruction at a time. We have seen the basic operation of the computer, which going to be fetch the set of instructions which are submitted in a program. So the processor will consider or bring one instruction at a time and perform operation specified. So that instruction comprises the operation and the operands. By observing the format of the instruction formats, so there we have the operation followed by the operands. So that operands may be 1, 2, 3 or no operand. Sometimes if you are talking about a zero address machines, that is a stack based machines. For example, add a comma b, right? Add is an operation, a and b are the operands, right? So like that operation, what operation specified there, so that kind of operations going to be performed here. So instructions are fetched from the successive memory locations. So the program stored in a memory, so the sequence of instructions are going to be bring to into the CPU premises through the processor and other component. So especially when your instruction fetching from the successive memory location until a branch or jump instruction is encountered. So if no branch or jump instruction in the program, then it will be instructions are successive memory keep on accessing and bringing those instructions. Wherever the branch and jump instruction encountered, that program counter PC has to be load the target address of that branch or jump instruction where it is reside in the program, right? So if not, then it will be normal flow will be continued, that successfully accessing those instructions in the successive memory, so on. The processor keeps track of the address of the memory location containing the next instruction to be fetched using a program counter. So that program counter is a register which situated in the CPU premises, which is always hold the address of the current instruction. Once the current instruction is handed over to the processor, and it will point to the next instruction in the sequence, and suitably it will be advanced by word length of the computer. So it's 16-bit machine may be talking, so 2 bytes will be advanced. Similarly 32-bit operating system or 32-bit instructions are handling, then that program counter will be incremented by 4, right? So on, it depends upon the architecture, the program counter value going to be advanced or increased. So that is an instruction set register. Instruction register is there. So one more kind of register is in the CPU premises that going to be hold the instructions at the CPU. So once the instructions bring from the memory, right, instruction bring from the memory, and it has to be rushed to the CPU, where somebody has to be locate them, somebody has to welcome them, and provide the space. So one such register called instruction register, which will welcome the new instruction which you enter into the CPU or processor premises, so that IR instruction register will welcome it and store there, right? So that is a sequence will be going on once that instruction come to CPU premises. So let me see instruction execution, how it will be execute the instruction. So fetch the contents of the memory location pointed by the program counter. So what is a program counter? It holds the current address of the instruction. With help of this address and through the MAR, memory address register, it will go to the memory, where it will search that location. After finding that location, the address which is provided in MAR, and that current instructions will bring downloaded from the memory, and place on the databus which has to be traveled, which is going to be reached to the CPU premises or processor. So that will be fetching the contents of the memory location, which is pointed by the program counter. The contents of this location are loaded into the IR. Contents of this instruction are loaded into IR. What is IR? Instruction register. So once the instruction arrive at the CPU premises, I told somebody has to be welcome and provide a space, so that IR will do that. So that is a fetch phase. So that contents of the PC will go to the IR. So what is a PC? It is a current address instruction. So the contents of that contents at the memory location will get a data or instruction which is going to be bring it travel across the bus which is in the CPU premises, and it has to reach to the CPU premises, and there somebody has to welcome, that is IR going to be placed for that. So instruction register, that is responsible for also fetch phase. Assuming that memory is a byte addressable, right? So memory is a byte addressable. So increment the contents of the PC by 4. Byte addressable 32-bit, then it is a 4 bytes. So that will be PC will be going to be advanced by 4, so that it can point to the next instruction. So it currently it brought the first the current instruction and hand out to the MAR and system. Then with help of that from the memory it brought instruction, it is there IR. Now the responsibility, the program counter should be self increment will happen, so that it going to be point to the next instruction, get ready, right? It going to be point to the next instruction. So that is a PC equal to PC plus 4, right? So carry out the actions specified by the instruction in the IR execution phase. That is a fetch phase. Instruction brought into CPU, and it is at the place of the IR. Now that phase space is complete, so execution phase will be commenced. So carry out the actions which is specified by the instruction. So instruction is you have to explore, there contains the operation and operands, right? For example, add a comma b I told. So add is a arithmetic operation, a comma b is a operands, right? That actions will be specified instruction in the IR. So that is execution phase. So we need to be understand the semantics of that arithmetic operation or logic operations which is specified in the operation space, and followed by the operands options also there, right? If operands, for example, add a comma b are the operands. Suppose the complement a, so a only one operands will be there, complement is a operation. Similarly, several operations may be possible, so that execution, from the execution phase we will understand that meaning of that operation. So processor organization, right? So we are able to discuss so far the instructions we are bringing by the guidance of the program counter and go to the memory. So we bring that instruction. So once we bring, then it will be placed at the IR. In the meantime, automatically the program counters would get ready to catch hold or point the next instruction in the sequence. So that will be performed automatically. So once we brought an instruction at the CPU processor level, so there we will be able to understand the instruction by exploring that, understanding those instructions operations, right? So that actions will be taken place. So those are the concepts we discuss. With help of this foundation, let we begin how this organization will be happen, right? Processor organization. So let we consider single bus organization for of data path inside the processor. So inside the processor we have a circuits, right? So that we call as a data path. So the how single bus organized to bring out as a certain data path inside the processor, which comprises the internal processor bus, right? So here we have the long bus is there here. So what is a bus? Bus is a collection of wires which carries the data, instructions or control and address, right? So data, control, control information, address information. So for example, control, read and write, the IO read, IO write, so on that. So address will be there, and the data will be there, right? So these three signals will be carries through the internal bus, processor bus, right? So from this we'll try to explore the how the single bus will be organized of a data path which inside the processor. So as we told, that is a program counter, is a simple register which holds the address of the current instruction. So job of this is always point to the current instruction. As soon as submit the current instruction, it is to be self automated, so it be self incremented and automatically point to the next instruction in the sequence. So the length of the instruction, the program counter depends upon the architecture. There is maybe 8085 with maybe the 8-bit, maybe 8086 we have the 16-bit, right? So on that it depends upon the architecture, the length will be specified. So we have one more register called MAR, memory address register. So memory address register, the program counter value will be put into the MAR. So it go that directly the link with the memory. So it goes to via address line. With help of this address line, it go to the memory. There it will be search that location, and once it is available, and it will load on to the data bus or instruction bus, which is going to be reached to the internal processor bus, right? So there here IR will be welcome that we just discussed in the previous. The MAR going to be address register, and we have one more called MDR, memory data register. So if the instructions or data is there in the memory, so if you pointed by this MAR, and that corresponding data has to be put on to the data bus, and it has to be travel across the bus and reach to the processor. When you reach the processor, somebody has to welcome that data, so that MDR will do that. So MDR will welcome that data and provide a space for them to stay here for some time to execute that, right? So that is a data lines. So MAR concerned to the address lines, right? So I hope you following. So the long bus will be there, internal processor bus. For that PC will be connected, that is a bidirectional, and we have MAR, it is a unidirectional from processor bus to MAR. So the address will be roaming here from the PC. When you make a PC out, or PC will be generate produce that address, it will be roam across the bus, and somebody has to be interested on that, they will welcome that, so they will accept that. So a PC will be send the data or instruction, sorry, address of the instruction, and it will be roam here. So somebody has to welcome. During that time MAR will welcome, and it send in address. Similarly, after searching in the memory, and it will be the data will be uploaded onto the bus, and it has to travel and reach to the processor. When reach the processor, MDR will be receive that, right? So similarly, so these two called, we can call it as a memory bus. So these are address bus, address lines and data lines, MAR and MDR, will connect it to the memory bus. Similarly, there is other bunch of registers are there for the make use of some temporary operations, or we can store some intermediate results. So for which set of registers are there. So there is R0, R1, R2, up to Rn minus 1. So the bunch of registers are there. So these are general purpose registers. So this programmer can use these registers and make operations. You can use for temporary storage, so on. That is, apart from this, there is a one more register called temp. Temp is a temporary registers. So these registers are small buffers or small file, which length of register again depends upon the architecture. So it maybe 8-bit processor, so 8-bit, and 16-bit processor, and this may be 16-bit length, so on. That is, so right. So register we understood, and there is a temporary register, and as we see in the previous discussion, once that bring an instruction to the CPU premises, so that will be somebody has to welcome the instruction. If it is data, the data that MDR will welcome, even data or instruction will welcome here, and it has to be put it to the processor bus. It will be travel across the bus, and somebody has to welcome. Who will welcome? IR will welcome. Instruction register will welcome that, right? So after welcoming that, it will be start understanding what is that contents. So if it is an instruction, then we need to be explore that what is operation, what are the operands. So instruction decode will be there, right? So after decoding the instruction, so it will be understand what kind of control signals we need to be generates, whether add operations, load operations, store operations, multiply operations, so on that. So there is a memory read operation, so on that. So this kind of semantics will be bring out after decoding this, and with help of the control logic, right? So these are some necessary registers which will be there in a CPU premises. Let coming to the arithmetic and logic operations. How logic, arithmetic and logic operation will be happen. So there is a arithmetic logic unit. So this have two input called A and B, right? So and one output that may be a Z, right? So this is the arithmetic operation block. So which generates it receives some operands, and it will perform some operations and produce the output, and push out to this output into the general bus, that is a internal processor bus. So in that sequence, let we see what will happen, right? So there is a B register, B point connected to direct to the bus, B connected to directly to the bus. Whatever the data rushing roaming in the bus, so that will be automatically rushed to ALU automatically, because it is no control valve here. So it will be directly connected, it will be directly rushed into there. So other one should become via Y register, right? So Y will be connected to that bus. So whatever the data is moving here, that will go to the Y also. It will go to the Y also. And we have, that is a multiplexer. So multiplexer will have two inputs. One is called constant 4 and Y. Why it is a constant 4? So as we discussed that advancement of the program counter, automatically it will be for every instruction execution, that program counter will be advanced itself automatically. So that it will increment by 4 bytes if it is a 32-bit machine. If it is 16-bit processor, it will be increment by 2, so on that. So right now let we consider 32-bit, and it will be advanced by byte addressable, so constant 4. So 4 will be advanced. So here, so the this two data rush into the multiplexer. So any one will be get select, either constant 4 or Y, right? So select symbol will be there, either select the constant 4 or Y, any one will get selected, one will be eligible to rush into this ALU part, right? So either Y may come or constant 4 may come, right? So let we see, anyhow the data which is rushing, roaming in the processor bus, that will be automatically get into here. So A and B. So once this A and B are available at this premises of the ALU, that they are going to be perform some arithmetical logic operation, right? So that result is going to be placed in the Z register. So Z anyway connected to the bus, so that will push that content, that the resultant value will be pushed into the processor bus. So somebody has to welcome who have need that, who have instructions. In the instruction itself, they specified the destination, the register or destination address. So that register will be eligible to receive that. So if we are performing addition subtraction operation, then there is a carry in carry out will be there. So there is a different type of arithmetic operations possible: add, subtract, logical operation, XO, XR. So these are the ALU control lines. So once this is the control signals will be decoded instruction, and this the control signals will be connected to here, right? So that is after understanding the instruction from the IR, we can able to understand what arithmetic operation, logic operation will be mentioned in the instruction. So that signal will be connected here. So according to that, the arithmetic or logic operation will be happening here. So if it is a addition, then carry will be required. So that carry will be considered. So finally, Z value will be produced, that is right. So here coming to it approach to the bus. It approach to the bus. So from this discussion, I hope it is clear about single bus organizations, the data path which is happening inside the processor, right? So MDR has two inputs and two outputs. So MDR we can discuss in the due course, because the MDR connected either side the internal processor bus and other side memory bus, right? So it has to be talk with the memory, and also it has to talk with the processor bus. So that's why that two outputs will be essential for in and out towards the memory bus, and also in and out towards the processor bus. So to each outputs will be there, right? So execution of an instruction, let we see that. So transfer a word data from one processor register, one processor register to another, to ALU, right? So perform an arithmetic or logic operations, store the result in a processor register. After performing logic or arithmetic operations, so result will be going to be stored somewhere, where here that is especially in the processor registers. So general purpose registers we have understood, that is R0 to Rn-1. So those will be involved there. Fetch the contents of the given memory location and load them into processor register. Fetch the contents of the given memory location. So that is the instruction which is pointed by the MAR, intern PC, program counter. So that program counter tell to the MAR go to the memory, there it will be identified, and once identified, it load on to the it has to be sent to the processor by loading onto the bus, that is a memory bus, and it travel across the memory bus and reach to the processor. There has to be welcome by, that is a MDR or IR. So let we see when IR and MDR will be happening. Store a word of data from a processor register into given memory location. So register transfers, so the gating for the register will be happening here, right? So register transfers will be taken place in the CPU premises. So let we see the internal processor bus, as we see in the previous discussion. So the internal processor bus will be there. So we have a general purpose register called R0 to Rn-1. In there we take an example of RJ, right? RI or RJ, RI we can take it. So RI is connected to the bus. So for if you connect directly, then anybody can, any data may be rushed to this RI. Instead of doing so, we can put some control valve. So that is a gate will be fixed here. So RI in. So RI in enable. RI in enable means what is the data roaming in the bus. So that will be entered into the RI. If RI in is disable, so means gate closed. Gate closed means so no data is rushing from the bus to RI, right? So if it is RI in is enable, so data is there in a bus which is produced from some other registers or arithmetic operations, and it will be bring to RI, because this gate is open. So since gate is open, the data will be rushing automatically to the RI register. If it is disable, then no data will be entered into the RI. That's all. So similarly, if the contents of RI you want to send to somebody or put it onto the bus, So from the bus somebody will take it. So we can ri out make it enable. This control valve will be make enable. So the contents of this ri will be coming out from the ri and enter into the bus, enter into the general bus, that is a processor bus. And where maybe need or some register mentioned in that arithmetic instructions, so that who will be those will be welcome, that is. So I hope you understand. Ri in is enable, data will be received from the bus. Ri in out enable, the contents of the ri will go to the bus, processor bus. If it is disable, no operation, no transfer of data will be happening. Similarly, we have discussed the arithmetic logic unit, that is a ALU part. So there we have two registers called Y and A, that is A and B, right? So A will be received from the Y register, so there is a Y control valve will be there, so the gate will be there. So Y in enable, if it is, then the data which is roaming in the bus, that will be rushed to the Y register. So Y register is Y in enable, then Y will be able to receive that. If not, Y is disable. So Y in is disable, then no data will rush to the Y register. So once it is Y, we have seen in the previous discussion. So that is a ALU have multiplexer. So multiplexer will have two inputs, one called constant 4 and Y, right? So there is a select button will be there. So that select button that will be select either constant 1 or Y. Any one will come out. Any one enter into the mux, and from the mux 2 it will go to the ALU. So where A either may be constant 4 or Y, the data will be there. Anyhow, B directly connected there, and I hope the two data is ready to enter into the ALU part to perform some arithmetical or logic operations. It happen, right? So then once the result produced, it is going to be stored in a Z register. So in order to reach the Z, there is a Z enable will be there. So Z enable gate will be opened or enabled is there, and only that data will be travel to and reach to the Z register. If not, it will be stationed at ALU itself. It will be stay at ALU itself till that Z in enable happen, right? Z in enable happen, only that results which will produce from this ALU part will going to be produced or released from the here, and it reach to the Z register. Once it is Z registers hold that data, and there is a Z out enable maybe is essential. So Z out enable is performed, then only the content of the results or Z value it going to be general bus, that is a internal processor bus. Otherwise will be stated at Z also. Let us assume that Z out enable, then the content of Z will be moved to the processor bus, right? So after understanding this ALU part, let me see that how register transfer will be happening. So registers to registers, how data will be transferred. All operations and data transfers are controlled by the processor clock, right? So let me see input output getting for the 1 bit register, one register bit we'll see that. So there is a D flip flop which help us to store the data. It will keep the data and it give it as it is when the clock supplied, right? When you clock supplied, so whatever the data is coming, it will be stationed, it will be produced. The clock is disabled, no data will be stationed here, so some data will be locked here. So clock is 1, so if you supply 1, 1 will be maintained and will produce. If you supply 0, 0 will be maintained, 0 will be produced. That is a property of D flip flop we have discussed, right? So let we see to construct this getting the what we seen, that in and out enable, register in, register out, and various in and out signals will be there. So that can be performed with help of this D flip flop. So we have D flip flop, that Q will be connected to the bus, right? So not bus, that is. So we have that is a mux multiplexer. So multiplexer receive 1 and 0. 1 is coming from the bus and 0 is coming from this side, right? So the multiplexer will allow any one. So depends upon the in, that is the in. This is a on behalf of register, on behalf of any component which be seen in the processor. So that enable, how in enable happening, how in out enable out enable happen, and also disable happen, right? So for example, we can see that RI. So this is for RI circuit, register RI in RI in is enabled here, so that is a 1, and it will be go to that D flip-flop, and it will be make out and reach the 0, and we have that is a what is called RI out. So this is a tri-state buffer, that is a controlling here tri-state, that RI out is given here. So RI out is 1, and whatever the data is there, it is coming out. If it is RI out is not enabled, and data will be locked here, right? So that data will be locked here, so that we can see that. So this is a in and out signal will be performed with help of this D and multiplexer used for the data transfer or controlling by the processor clock. Performing an arithmetic and logic operation, let me see. So the ALU is a combinational circuit, means it doesn't have any internal storage. So ALU gets the two operations from the mux, multiplexer and bus. So the result is temporarily stored in a register Z. We have seen that result stored in a temporarily register Z. What is a sequence of operations to add the contents of register R1 to those of R2 and store the result in R3, right? So the store the result in R3, the contents of R1 will be added to contents of R2, and result has to be stored in R3. So this we need to be performed by this signals. We can let me see that. So the at clock pulse T1, R1 out. Once it is R1 out happen, the contents of the R1 data, it is moved to the processor bus, and it roam across the bus, and where may we need they will welcome by their in enabling. In such case here, so Y register make in enable, maybe in the future plan. So that ALU, because Y is one of the input for the ALU, so it is planning that R1 is pushing to Y register, and other value may be directly coming from the bus, so that R2 out. So R1 we are intending to perform R1 addition with R2, then result going to be placed in R3. In that sense, one operands we brought into the Y, the other operands we are planning to bring into via B, right? Via B, that is R2 out, select Y, R2 out, select Y, right? So R2 out is means it push the data into processor bus, right? R2 out. So R2 out made the processor will hold this information of this, and who will be by default make in enable. So that is a B register. So that is B point at the ALU junction. Which is always enabled. So it automatically it rush to the ALU via B point, right? So through A point it will be select Y is there, no? Select Y. Since select Y are constant 4, we can either one we select, no? So here we want to perform this addition operations. So that too we have already dumped R1 into Y, no? So that's why select Y. I will follow select Y. By selecting Y, then one operand is that is a R1 on behalf of R1. So Y is representing now. So add, right? Add means what? One operand via Y, the other operand via B point. So that will anyhow it is roaming in the bus, it will be by default it will rush into the ALU through point B, right? So R2 out, that is R2 out, add, and after performing addition, then result we have to place at the Z register. So Z, instead of saying Z, we can say Z in enable, so that it will be produce the result from the ALU junction. It will be push out from that ALU and placed it in the Z register. So that is a Z in register. So once it is available at the Z in, then we have to push into the destination. What is a destination register? R3, right? So Z out. Once you make a Z out, what will happen at the clock pulse 3, right? At the clock pulse 3, the 3 steps indicates the clock pulse 3. At the clock pulse 3, the contents of the Z value will be pushed out and ask them to roam at the internal processor bus. Once it is roaming in internal processor bus, somebody has to be welcome. If nobody will welcome, it will be rushed into the what is B point at the ALU. So in order to avoid that, somebody has to welcome, somebody has to receive that. So here need, that is where we need means what resultant operands may mentioned in the instructions. So that is R3. Also R3 will be welcome that, right? So before getting a B or with the tolerance time, so R3 will welcome and code that result. So this is simple arithmetic operations will be happening with help of the register transfer mechanism, right? So let me see fetching a word from the memory. So fetch the word from the memory, that is address into MAR. So contents of the PC will be written to the MAR, right? So issue read operations, so data into MDR. So issue read operations, data into MDR. So connections and control signals for register MDR will be happening, that is. So let we see that internal processor bus. So internal processor bus connected to MDR register, so through MDR in. So MDR in enable we have to make it, so it will go to the MDR from the processor bus. So if it is a MDR out, it is also possible. So that is that is a MDR bus. MDR out is there, so that gate we have to make enable, so it will be rushed there. And similarly MDR out enable in the sense towards the memory bus, it is towards the memory bus, it is towards the processor bus, right? So differentiates this MDR out towards the processor bus and towards the memory bus. So we can discriminate then MDR out E and MDR out. So MDR out in the sense that it is towards the processor bus. MDR out enable the external, or the MDR out external, so that is towards the memory. So that is a memory bus, data lines will be there from memory bus, that MDR in external. So this is the discriminated with help of the MDR and towards the processor. So this mechanism will be there whenever read and write operation through to the memory, right? Fetching a word from memory. So response time of each memory access varies. Cache miss, memory mapped IO. So the response time will be varies. So here to accommodate this, the processor waits until it receives the indication that should be required, whether the data has arrived or not, so that operation is complete or not. So requested operation has to be completed, so that is memory function completed. Whenever we initiated the memory read operations or memory write operation, since the memory is located outside the processor premises, so there and also it is a it have inherently some problems. So especially that is a electromechanical device, so that may be inherently slow. So that for that we need to be any acknowledgement, any operations initiated, for which we have to wait for certain amount of time to complete that operation, that is called MFC. So move R1 comma R2. What is R1? So the R1 is a content of the R1, so bracket will be there. So move contents of the R1 to R2 means, so the R1 have some address, so that address, with help of that address we have to go to the memory and search, bring that content. So that is a read operations, right? Move the memory, move the contents of the R1 and put it into the R2. So that is a memory read operations. So put the R1 into MAR, put the contents of the R1 into MAR, so it search in the memory and start read operation in the memory bus, right? So wait for memory function completion, response from the memory. So since we have in the previous clock we initiated the memory related operations, we are initiated the memory related operations, so we need to be give some certain time. So till we have to wait till that completion. So we should be get some acknowledgement. So response from the memory. So load MDR from the memory bus. Load MDR. After reading that data, we have to load to the that what is called external memory bus to MDR. So that we have to be load, that is. So the R2 will be receive that MDR. So the intention behind that, move contents of the contents R1 to R2, right? So that is a memory read operation. Since memory read operations, the procedure we need to be sequence we need to follow. R1 has to be copied to the MAR. So start read operations, wait completion of that operations. Once it is completed and the data is ready on the memory bus, it has to be travel and it has to reach the MDR. So that is a load MDR from the memory bus. So once it is available at the MDR, then bring to it is MDR is situated in the processor premises, so that copy give to the R2, right? So R2 is a destination register which is specified in the instruction, which is specified in the instructions at move round bracket R1 and R1 bracket closed and R2, right? So let me see further, that is a memory read operations timings. So there we have simple operations, we have seen that register transfer. So we can see the some more detail about the read operations, that is. So that is a clocks will be there. So clocks, so there is a one clock, then the multiple clocks and third clocks. So that is a fetch phase, execution phase, and write results and so on. Several phase would be there. So again depends upon the architecture. So here MAR in we receive the PC value, so it is a 1, right? So the next we can have, assume MAR is always available on the address line of the memory bus. The responsibility of the MAR has to be hold the address lines, right? So it junction with an address lines. So MAR, the condition of the R1 goes to the MAR, right? So we have the address bus. So address will be decoded, and once the address will be decoded after this first clock cycle, and we will be able to understand which address in the memory, right? So we have a read operations we need to be initiated. So in order to fetch that instruction we need to be read, right? So after reading that, to start read operation on the memory bus. So there is a memory read will be commence. So it will be begin after the first clock at the beginning of the second clock pulse. So memory read operations will be happening. Similarly MDR in external, once the instructions read in the memory, it has to be load onto the memory bus, and it has to travel and it has to reach to the MDR. So how we can welcome that MDR? Instead of saying MDR in, we have to say MDR in external, because it is coming from the memory. So we have to MDR in external should be enabled. So after making that, we need to be anyhow we have to get a certification or completion certificate from that memory devices. So memory function completion. So that memory function completion may be received after the what is called first, second, third. At the end of the third clock pulse, we may able to get, because here two clock pulse, 1, 2, 3, 4 clock pulse merged here. So end of this clock pulse, we are able to get a memory function completion. Wait for memory function completion response from the memory, since there is it is situated outside the processor premises. So once updated, completed, and data has to be arrived. So MDR is already making that preparation. So load MDR from the memory bus, right? So MDR out will be there. So once it is MDR is copied or stored that via MDR in external, so now we have to make it MDR out. MDR out in the sense it is to be pushed out to the what is called R2, right? So R2 we have our plan, that is, so the content of R2 now the contents of the MDR, right? So this is a memory related operation. Earlier we discussed what is called register transfer operations. So after getting some full-fledged knowledge, let me see that execution of the complete instructions. So add R3 open bracket R3 close bracket comma R1, right? So you can see this instruction. So add round bracket R3 comma R1. What is its meaning? So R3 have some address. With help of that address we have to go to the memory. So that is the indirect address. We have to go to the memory. There we have to search that location and bring the data, that itself the data for R3, right? which indicates round bracket R3 is the address of the address of that operand. It is showing that is here memory read operation. Memory read operation is essential here. Memory read operation is required here, right? Because R1 have directly that data. The contents of the content that R3 should bring and get added with R1 and place the result in the R1, right? That is the semantics of this arithmetic operation. Let me begin how it will happen. Fetch the instruction. By fetching the instructions, we are able to understand the meaning of semantics of that instruction. So fetch the first operand, the contents of this memory location pointed by the R3. So they perform the addition operation. Once we bring that content of the R3, so load that result into the R1. After performing addition operations, the result we going to be stored at the register R1. That is going to be performed. That is. So let me see how it will be happen. So we have discussed enough about this the data path of the single processor, single bus organization. We discussed in the previous the slide. So the same diagram is repeated here. You can see the general bus and processor, program counter, MAR, MDR connected to the memory bus, and the IR connected to instruction decodation, and bunch of register R0 to Rn-1 temporal register, and the major part is the ALU, which will receive two inputs called A and B. So A will be junction connected to the multiplexer, either Y or constant 4, which will select by this. So during program counter advancement, during that time the constant 4 will be involved. Otherwise, in all other arithmetic logic operations, Y will be involved and rest to point at the A to ALU. The any data which is planning to without sending to any register which is roaming in the bus, so that will be automatically rushed into the point of the ALU and involved in arithmetic or logic operations. And these operations will be, the output will be held at Z and will be connected to here. We also discussed the Z in and Z enable, Y in and Y enable, any general register R in and out register, MAR in and MDR in and out also. Anyhow, so we have built some fundamental concepts. So let me begin some execution of the instruction. So the steps involved here. So there is actions. So we have the first step at the clock pulse T1, PC out. What is a PC? PC is a program counter, contains the address of the current instruction, which is going to be bring out. And once we bring out, where we have to store, we can store in a MAR, right? PC is a bidirectional. It is once you PC out, the address will be roam here, and it has to be welcome who? MAR in welcome, that is MAR in. I have followed. So after bringing that MAR, then it is a planning to read operations, right? Is understood when we are putting something in the MAR. So we are going to be initiate some memory related operation. One such operation called read operation. Select 4. You can say select 4, right? Select 4 means, so we are planning to advance the program counter. So automatically it has to perform. No? So let it happen, the read operation, let it happen in the background. So now it is a processor free. So what we have to do for that, this time we can make use for advancement of the program counter, so that it will point to the next instruction in the sequence of the program. Select 4 add, right? Select 4 add. So add means multiplexer will allow constant here. What is a B point? B will receive the old value of the program counter, right? Anyhow PC out is made now, so PC out still that copy is roaming here, right? So one copy may be received MAR, the other copy, that is replica, will be roaming in this processor bus. So we can make use that, ask them to welcome via point B to ALU, so that we can make the automatically advance the program counter, right? So I hope it is followed. PC out, MAR in, read, select 4 instead of Y we selected because we are planning to advance the program counter. Add Z in, right? So Z out, PC in. Z out means what that is. So after performing addition operation, the contents of Z will be hold the results. So this we have to safely keep it back in the program counter. So that's why PC in, right? So by doing so, what will automatically program counter will be advanced by 4 at the second clock pulse, right? PC in. So Y in, wait for memory function completion. So what is that Y in? That is, So y in may be for the next operation, it will be getting ready, that is so z out pc in, wait for memory function completion. Once the memory function completed, then the instructions which you are planning, this is addition operations, so that will be bring into the MDR. So once it is memory function completion, then it automatically understood that it always it brought that instruction and store at the CPU premises and the location of the MDR. So now we have to bring out that, so MDR out and IR in, right? So that this complete instruction, it at the MDR, now we are making it and place into the IR, instruction register. So instruction register will be holds that instruction. So this first three steps we can call as a fetch phase. Once it is a fetch 3 steps is completed, the 3 clock pulse will spend. So now assume that the complete instruction is available at the IR. So now we have to be decode that and understand what is the semantics. So either maybe add, subtract, XOR, so on, that is. So R3 out, MAR in, right? So R3 out, MAR in, right? So that R3 holds some operands, right? So that that we need to be bring MAR in and read operation, right? Since that is a indirect address now. So R1 out, Y in, R1 out, Y in, Y R1 out. So other register value, no? So that register value we have to be add the contents of the content with R3, right? So that anyhow that R3 contents will coming via Y, R1 out, Y in, sorry, R1 out, Y in. So R1 out is coming planning to rush into the ALU through Y junction, Y, that is a wait for memory function completes. Why? Because in the previous we have initiated the read operation here. So previous we have read operations we instituted, because this is a indirect addressing. So that's why we have to get certification from the memory. We have to get a green signal from the memory, that is wait for memory function completion. So once it is completed, MDR out. So it means so that data has arrived. Data has arrived to the CPU and it will be make out to the processor bus. It roam here. So select Y. Select Y means R1. Select Y means R1. The other R3 will come at a MDR, right? So both will be rushed into the ALU. So ALU, I hope followed, that is what is a B. B will get MDR out, no? MDR out, what is that? Contents of the R3, right? So that will be rushed into the ALU. What is a Y? Y is R1. Y it is R1. Both are arrived here and the ALU as per the instruction of this arithmetic. So add operation will be happening. Once the add operation will be happen and stored in the Z register called Z in, right? So Z in will be holds, that is. So once it is Z in is available and bring out them and store into the resultant variable called R1. So Z out, once you make it Z out, it again it roaming in the bus. Somebody has to welcome. Who will welcome? The destination register according to this instruction is R1. So R1 has to be welcome. So this person has to be welcome and keep the copy. And by the end of this the clock pulse 7, the instruction execution is completed. I hope repeat once again. The first 3 steps reserved for the fetch phase. Remaining 4 steps will reserve for execution. The here will be bring the instruction as well as the advance the program counter. That automatic increment of the program counter is also happening here, because whenever read the memory operations, during that time the processor will be do not have work, that for which, because we are waiting for memory completion. So meantime we can do some other operations like program counter advancement. So that will be happening, that is. So from this I hope you will clear. So let me see one more example, the branch instruction. So branch instruction replace the contents of the PC with a branch target address, so which is usually obtained by adding an offset X given in the branch instruction. So the branch instruction encounter, it means that control will transport to the target address after adding some suitable offset to, and it will be able to find out the target address. So the branch instruction, the offset X is usually the difference between the branch target address and the address immediately follow the branch instruction, right? That address need to be found, and there is also conditional branch. If X is greater than 0, then branch, or sometime it is depends upon some flags value, depends upon the conditions it is satisfied. then branching will be taken place, jump will be taken place. So execution of the branch instruction, let we see control sequence for the unconditional branch instruction. So there is a stacks actions will be there. The first step will be, as we discussed enough in the previous slide, that related to the execution of the instruction. The first three steps are related to the fetching up an instruction. So that in that sense, the first clock pulse, the PC out and MAR in, read, select 4, add, Z in, right? We discussed in length in the previous discussion. And the second clock pulse, that Z out, PC in, Y in, and wait for memory function completion. That is a advancement of the program counter. Once it is happened, memory function completed, and receive the instruction, that is a, we have planned to execute the branch instruction, the MDR out and IR in. From the exploring the IR contents, we are able to understand whether it is a branch instruction or not instruction, or any arithmetic operation. So here we are discussing anyhow that branch instruction. Let we assume that the IR holds the branch instruction. If you know that, then branch you need to be select, branch address you need to be select. So for that we have offset field of IR will be there. So after exploring the complete IR, we are able to understand the arithmetic operation and operands and offset. So offset field of IR can be bring out and add to the add with the what is called the earlier value, that is the PC value. So it is a PC value. Z out will be there. So the program counter value will be added and able to find the target address in the Z in. So Z out and PC in. So PC holds the address of the next instruction. Here in this sense, the target address. So PC in holds the address of the next instruction, that is a target. So that is a jump instruction where it will be commence the execution, right? So normal execution will be suspended, need to go to the there, and it will be commence the execution there, and it will be end, that is. So that this is the control signals for the jump instruction is similar to the quite similar to the previous discussion what we discussed. So similarly, this can be also happen with help of the multiple bus organization. One such example called 3 bus organization of the data path. So let's say a bus A, bus B, and bus C, right? So with help of three bus, we can see that there is a increment, a program counter. So program counter will be there. So additional important, that is a incrementer will be there. So increment by 2, increment by 5, 4, increment by 8. So it all depends upon the architecture. So that is an incrementer, additional register will be there. So there is a register file. Register file is you can say that bunch of registers in the previous architecture. That single bus we have seen the R0, R1, R2, Rn-1. So all those comprises we can call as a register file. The bunch of registers will be there, and of course the ALU part will be there. So ALU part, here we have A point and B point. The B point is connected to the B bus and A point is connected to the A bus. So that is a via mux will be coming, and result will be produced and it connect to the bus C. And we have a instruction decoder from the IR. So IR will be, bus C will be connected to the IR, and instructor decoder will be, after decoding it, will send to the bus A connected to that is what is called the ALU, right? So bus A connected to the multiplexer, right? So here we have MDR. So MDR is connected to the bus C. We will welcome and produce the output and set to the both bus called A and B. So we have memory bus is data lines are connected. So MAR is connected to data address lines which connected to the bus C, right? So control sequence for the instruction, let assume that add R4, R5, R6. The example, add R4, R5, R6 for the 3 bus organization. How this addition will be happening, let we see. The action steps are, so PC out, R is equal to B, R is equal to B, that is a bus B connected here. So MAR in, read, increment PC. So the little improvement over the automatic increment of the program counter, let we can see here INPC, whereas in the previous case we have length of instructions or other micro operations were involved there. So since the multiple buses are there, so incrementing program counter by default will be happen with help of this register, right? So R is equal to B. What is R is equal to B? So register connected to the bus B that is. So wait for memory function completion, because MAR involved here, memory related operations. So we have the once completed, MDR out B, MDR out B. Here MDR out to B bus, B bus. So then R is equal to B. So R is equal to B. R register file will be receive the data from the B. So IR in means instruction register. So we can have R4 out A, R4 out A, R4, where is R4? Here register file. So out A through bus A, R5 out B. So out B. So 1 to bus A, 1 to bus B. Select A, right? So here we have multiplexer. Select A and add. So one is at A, one at B. Select A, then it will be avoid the constant 4. It rush to via mux to A and B arithmetic unit. So there we have to add and R6 in. So the here connected to bus C, no. So this registers file here. So R6 will be here in the register file. It will be welcome, and that is the end of the instruction. So from this, I hope it is clear about this how the control signals will be generated with help of this basic processing unit. So we have executed register transfer, simple arithmetic instructions. So that to indirect address we have make use, that is and also branch instruction, and the 3 bus multi-bus organizations we have seen. I hope it is understandable, and the reference books are Karl Lemaitre, Rancic, Jackie et al. Computer Organization, 5th edition, Tata McGrail. Second book, William Stalling, Computer Organization Architecture, 9th edition, Pearson Education, and also other books also there. Thanks to coordinator, moderator, and subject expert. If any queries are there, please post to this mail ID. Thank you.